This video is meant to introduce you to the physics concept of current and things related to current like current density and drift velocity. We'll start with the definition. The physics definition of current is the rate at which charge passes through a cross-section of an object. Now we know anytime we see that phrase, the rate at which, that means that we're going to be expressing our equation in terms of a derivative. So current, which uses a capital letter I, can be expressed as the derivative of charge with respect to time. This can be used regardless of whether current is constant or not. But quite often, when current is constant, or if we're looking for an average current, we'll use the change in charge divided by the change in time. Really, we're thinking about how much charge has passed a certain location in a conductor in a certain amount of time. You could think of that with an analogy. Thinking about looking at a bridge overlooking perhaps a highway. If you were thinking about it that way, it would be like counting the number of cars that pass under the bridge in a certain amount of time. You can get an idea that it has something to do with how fast the cars are moving. The faster the cars are moving, the more cars would pass beneath your bridge in the same set of time as if traffic was dense and cars were moving slowly. If we think about the unit here, charge we know is measured in coulombs, and time is measured in seconds. And a coulomb per second is otherwise known as an ampere, which we use a capital letter A for. Quite often we abbreviate that to say amps, but ampere is the actual full name of the unit. Now, to have an electric current, there must be a net flow of charges through a surface. So again, using my traffic analogy, if I had some cars going one way and some cars going the other way, we wouldn't really say that there's a current. We'd want to say that all the cars are moving in approximately the same direction. Some more facts about current goes with this comic that I have right here. Basically, the idea is that in a conductor, free electrons create a current because we know that electrons are the things that are able to move. However, unfortunately, the direction of current is defined as the direction positive charges would flow. You have Ben Franklin to blame for that. Basically, when he was first setting the convention for the direction of current, they had no idea about what electrons or protons were. We had no concept of knowing that electrons were the things that were able to move around and protons were stuck in the nucleus. Therefore, it was all Ben Franklin taking a guess as to what he considered to be positive charge and negative charge. He said that the one that was left on glass by silk was positive, while we have now learned that really that was a charge changing of electrons, and so we should say that it's negative. All thanks to the fact that Ben Franklin chose the wrong sign is the reason that we now say that it's positive charge is flowing for current, despite the fact that really it's the electrons that are moving. One last fact about current is that current is conserved. And we've talked of lots of other quantities being conserved, things like mass and charge and energy. The fact that current is conserved means that any current that's entering what we call a junction, and a junction is really just a meeting of two wires or two conductors, must be equal to the total current leaving the junction. In other words, if I have one wire and then it splits up into two wires, whatever current is entering here, let's call that I1, would be equal to the sum of the two currents that are leaving. Let's call those I2 and I3. So I1 would equal I2 plus I3. That's what we mean when we say that current is conserved. One of the other things that we find to be useful when we're dealing with current is something called current density, or the current per unit area. We use a capital letter J for current density, and it can be expressed as the current divided by the area. Now, when we're talking about area here, we're really talking about cross-sectional area of our conductor. Cross-sectional meaning the area that would be perpendicular to the way that the current is flowing. The direction of the current density, which happens to actually be a vector, is the same direction as the velocity of the moving charges if they are positive, and opposite their velocity if they are negative. Basically, what we're saying here is that the direction of current density is the same as the direction of the current, even though technically current isn't considered to be a. Our last concept when learning about current is something called drift speed. We start with the fact here that when a conductor does not have a current through it, its conduction electrons, those are our free electrons that are able to move, they move randomly with no net motion in any direction. At any given point in time, some may be moving up, but then others are moving down. Some may be moving left, and then others are moving right. However, if there is a current, those electrons, they still move randomly. It's not as if they're moving in a straight line, but they tend to drift. So they move from one location to another. Here's what I mean by that. If I were to be able to see those electrons inside of a wire, for example, let's say I had a special microscope that allowed me to see these electrons. That doesn't really exist. We can't see them while they're moving, but we're going to pretend for a moment. This electron may follow a path that looks like the following. So notice that it's really not moving in a straight line. That comes from the fact that it's seeing all kinds of forces from all of the other things in this material, lots of other conduction electrons and atoms. However, it did eventually get from the left-hand side to the right-hand side. So it has what we call a drift velocity or drift speed, moving to the right just in general. We'll call that V sub D. And while it's moving relatively fast, as a matter of fact, electrons in conductors typically move on the order of 10 to the 6th meters per second, so quite fast. Their drift velocity is actually quite small, maybe only a few meters per second or even smaller. However, since we are thinking about this drift speed, we're thinking about them looking at kind of the average speed or the average velocity. So we know that average speed or average velocity can be expressed as distance over time. Let's say that section of our conductor that we're talking about has a length of L, capital L. So my electron travels a distance of capital L in a certain amount of time t. And we also know that if there's a current traveling, that again, we're going to talk about average current here. So instead of being the derivative dq dt, we're going to say that it's delta q over delta t. So if I solve this equation for time, I get that time is the amount of charge divided by the current. Put that into my equation for this drift speed. So I'd find that my drift speed is equal to the length of my section of times the current divided by the amount of charge travels. Now, I'm going to use an expression for charge. How much charge travels really depends on my material. And I could express that as the number of charges, or number of electrons really, times the charge on a single electron. So if I plug that in, I find out my drift speed is equal to the length of my conductor times the current in my conductor divided by the number of charges times E. Now, one thing I want to point out right now, this lowercase letter n means something different in your textbook than what I'm defining it as here. Here, I'm just defining n to be the number of charges. Really, the number of electrons is what I'm saying here. Lastly, I'm going to solve this equation for the current. And I find that the current is equal to NE times the drift speed divided by the length. Now, quite often, we're not really looking for the current, but perhaps we may just be looking for current density, or J. We know current density is the current divided by the cross-sectional area. So I'd have the number of charges times the charge on an electron times the drift speed divided by the cross-sectional area times the length. Hold on a second. When we multiply area times length, we call that something special. We call that volume. So I could write this as NE times the drift speed divided by the volume. Now, quite often, rather than saying the number of electrons or the number of charges, we actually have an expression for the number of charges per volume. On your equation sheet, they use a capital N for that. Sometimes it'll also be called the number of charge carriers per volume. This is a number that you can look up based on the material that you have. So copper has a different number of charge carriers per volume than aluminum, for example. That's what makes copper such a good conductor. It has a high number of these. So I could express my charge density as N, the number of charge carriers per volume, times E, the charge on an electron, times the drift velocity or drift speed of those charges. Or the way your equation sheet writes it, rather than writing it as current density, your equation sheet writes it as current is equal to NE CD times A. Because again, current density is I divided by A. So this is an equation that you are welcome to use. You do not have to go through that derivation. But it's important that you understand and know that derivation, as we may often be solving for something other than exactly the current, and you may need to explain kind of where that equation came from. So, to see how well you truly understand this, here's a problem. This problem asks how long it takes electrons to get from a car battery to the starting motor. Gives you some values, things like the fact that the current is about 300 amps. It's a very large current. That's why car batteries are really dangerous, and you want to be very careful not to shock yourself. We're saying that it goes through a copper wire that has a cross-sectional area of 0.21 centimeters squared. It's a pretty reasonable cross-sectional area for something like this. And it has a length of almost a meter. Since we're dealing with a copper wire, the number of charge carriers per unit volume can be seen as 8.49 times 10 to the 28th charge carriers per meter cube. Complete this problem on your own and bring your answer to class with you the next time we meet.